Hello students, after a long break I am again here. So basically today uh, deal with second law of thermodynamics and we will go slowly. I am not saying that I will be uploading lectures regularly because due to some reason or other I couldn't upload lectures regularly. But yeah, we will be finishing second law. Maybe if not today. Today I will complete the majority of the part, but some part will be left behind that we will finish on some other day. So now, second law of thermodynamics is somewhat a real law, somewhat not a real law. It basically deals with the real world or problems related to real world. Okay, like in first law of thermodynamics, it is said that the energy is conserved and energy can neither be created nor be destroyed. It can only be convert from one type of energy or from one form of energy to other. So there were many limitations in first law. I will be coming to that limitations points, but before that, let's see some basic things. Okay, see, second law of thermodynamics, as I've written here, it explains the real world or problems related to the real world. Basically, it deals with spontaneity. Spontaneity is nothing but it basically tells whether a process will takes place or not. Now see, this second law of thermodynamics is given by Clausius and Lord Kelvin. The other name of Lord Kelvin is William Thomson. Okay. Now see, there is one interesting thing. Okay, you all might know Stephen Hawking. Yeah, that scientist who was suffering from a very deadly disease, some disease related to motor neuron. Okay. So when he was, I mean, uh, dealing with his theory of time travel, the second law of thermodynamics was the uh, foundation of that time travel. This is a very interesting thing. You all can read all this thing in his book, or you can also Google it and you can also read. It is very interesting. If I get time, I will definitely explain this thing, time travel. Okay. Now let's see the limitations of first law of thermodynamics. Okay, it will be better if you write all these points with me. Okay, so let's go. See, the first limitation is that the first law of thermodynamics didn't tell us whether a process is spontaneous or not, or we can also say it like whether a process will take place or it will not take place. So in first point I'm writing, let me lock the screen. I'm writing, yeah. uh, First law of thermodynamics does not help to predict whether the certain process is possible or not. See, now basically, what is the reason? If I write the reason, it didn't say that heat don't, or sorry, it didn't say that heat cannot flow from a cold body to a hot body. He didn't specify all these things. Not he, the first law of thermodynamics, I'm saying. So I can write here, it does not specify that heat cannot flow from, I can write here low temperature body or cold body. You can write both these terms. Okay, low temperature body to high temperature body. Okay. uh, 1 second. Okay, now the second point is, the first law of thermodynamics also didn't tell us about the direction of process. I hope that you all know this first law. I'm basically writing the equation. It is basically delta U equal to delta Q plus delta W. But in some books it is also written as delta U equal to Q plus W. But I don't think that that is the right way of writing, because this delta or this d terms comes after differentiation. When you are differentiating, before every term there should be a small d, and if the difference is more, then you can replace it by a by this sign, by this triangle sign. Okay, so I think this is the correct way, not like this. You should not write it like this, equal to Q plus W. It basically makes no sense. Okay, yeah, yeah. So yeah, now you can come here. Second law, what I told you, that it didn't explain or it didn't predict the direction of the process. So I can write here, the first law does not give information about the direction. About the direction. Like, it actually puts no restriction on the direction of flow of heat, whether heat can flow from a cold body to a hot body, or from a hot body or from a hot body to a cold body. So actually it is like it's like it didn't say whether heat can flow from a hot body to cold body, or from cold body to a hot body. It was not specified. Yeah. Now what is the third limitation? The third limitation, you can find it very much similar with the first limitation, but I will explain one thing. Okay, see, in the third limitation I'm writing, it does not provide and specify sufficient condition this thing is important, sufficient condition for the process to take place. So here we are focusing on this condition wala part. Okay, we are focusing on this condition. Okay, the first law doesn't provide the condition upon which a process can take place. Okay, basically it didn't say anything. I mean, basically I can write this reason is that this law is basically silent about the percentage of energy that is converting from one form of energy to other. The law is silent about its percentage of conversion of energy from one form to other. Or here one more thing is there. Here we should be knowing this: work can be converted to equivalent amount of heat. But heat cannot be converted to equivalent amount of work. He didn't specify that. Why this thing happens? Because some heat, I mean, can get wasted. How it can waste it? By air friction or by any other means, by external intervention. You can write it like this. Now let decrease its size. Okay, I want to add some other points. Okay, okay, good. I can decrease a bit more. I think now it's fine. Yeah, I hope you all can see what I'm writing. Yeah. Now, in the fourth point, I can write that. So basically, the fourth point is based on the third point. The law is silent about the percentage of conversion of the energy from one point to other. So basically, if the percentage of conversion is not known, then the first law we can say that it is also was silent about the efficiency of the system. It don't say anything about the efficiency of the system. So I can write here that lacks information on efficiency. Efficiency we can write it by eta. Yeah. 5. The first law is only based on closed system. Yeah, remember, but in nature every time closed system is not seen. Open system might also be seen. Okay, yeah. Now, before coming to this part, I want to write some definitions. Okay. See, there are few general definitions of second law. We should learn this. So, basically, the second law of thermodynamics essentially says that in any spontaneous process, spontaneous as if the process that is taking place, in any spontaneous process, the entropy of the system and the entropy of the surrounding will increase or remain constant. Okay, so basically what I am saying that if the entropy of the system is increasing as well as the entropy of the surrounding is increasing, that means what? That means the total entropy is increasing, or the entropy of the or the entropy of the whole universe is increasing. That's what the first law, the second law says. Okay, so I'm writing this. The second law of thermodynamics essentially see, whenever I am talking about entropy, I will be dealing with this. Okay, now just write whatever I am saying. You all should have a basic knowledge about entropy because you all have studied all this in your junior classes, like in class 11 12th. Probably in class 11th there was one chapter related to thermodynamics over there. Entropy is nothing but the degree of disorderness, okay, or the degree of mixing, etc. If the system is more disordered, then the entropy of the system will be more. And secondly, note one thing: energy cannot be measured in absolute terms. I found it really very much disturbing when I saw that many of the teachers also write the energies in absolute forms, but that is impossible. Like we all have studied electrostatic in our class 12 standard physics. Over there was one term under the potential and potential energy part of electrostatics. Over there, to define absolute value of the potential energy, we considered one of the charge in infinity. By that only we can conclude that in this way we can say that the potential energy at a given point or the absolute value of potential energy is possible. Similarly, you cannot measure the absolute value of any sort of energy. The value that we can measure is the difference. Yeah, but mathematically we can write it like that. I'm not talking about the mathematical things, because mathematically you can write anything, okay, to prove anything. Yeah, but in reality you cannot measure the absolute value, you can only measure the difference. The second law of thermodynamics essentially states that in any spontaneous process, the total entropy of the system and its surrounding will either increase or remain constant. Okay, and this second law of thermodynamics is also known as law of increased entropy. Okay, now see one thing. We know that this universe has two parts. We all have studied all this. I'm writing in short. Our universe has basically two parts. Let's change the color. Okay. Universe has two parts. One is what? One is the system, other is the surrounding. Okay. Now it is saying that the delta S of the system will also increase or remain constant, and the delta S of the surrounding will also increase or remain constant. So basically this means that the delta S of the universe will also increase or remain constant. Okay. Basically what I can write, delta S surrounding equal to delta S system plus delta S surrounding. Sorry, over here universe will come. Universe, or I can also write it as a total entropy. Okay, now see, if I increase this thing and this thing, then definitely the entropy of the universe will also increase. Okay, I hope that you all get my point. Yeah. Yeah. Now let's come to the mathematical approach of the second law. See, here basically uh, a system is there. This is a system and this is also a system. So basically this whole thing is a system. Okay. Okay. Here a hot I mean body is kept, and here a cold body is kept. Or I can also say that it's a box and inside that a gas is kept whose temperature is higher, and here a gas is kept whose temperature is lower. So basically let it be T2 and let it be T1. Let it be T1 and let it be T2. Okay, this is hot one and this is cold one. So basically by the we know what conduction means. Now see one thing. There are three processes of heat transfer. I hope that you all know that. One is conduction, other is convection, and the other is radiation. Radiation and convection, especially this radiation is basically more over a physics part. I'm not going into that, and we don't need it. Here, what is happening basically is similar to conduction. Basically, what we can see here, heat is flowing from hot body to cold body. That's what you can see here. Yeah, I can write it also. Yeah, isn't it? And we know also, if you for example cook a vegetable over here and you put a spoon over here for some time, so what happens, and here fire is also there, so what will happen, as this utensil is hot, this heat will transfer from this part of the spoon to this part. So after some time when you will touch this part, you will feel the heat. Yeah. Now see, according to second law, for example here q1 is present and here q2 is present. I'm not writing that. So basically what we can see here, so basically we can find the delta q. Okay, so basically what we can find is the delta q. But one thing which is later you will understand that this is also a limitation of the second law. We have to deal with the reversible process only of delta Q. So basically delta is equal to delta Q reversible by absolute temperature. This is what you need to understand. You need to learn this, okay? You can forget everything, but don't forget this thing. Delta is equal to delta Q reversible divided by absolute temperature. If I ask you one thing, okay, let me ask this thing a bit late. Okay, now one thing, see. If I write here some energies, for example, delta G, delta H, delta S, delta U. Now you can, you try whether this energies or this change in energies are path function or these are state function. Try. Definitely these are state function. Definitely these are state function. What a path function? That depends on the path. For example, heat capacity, work, these things. But energies are truly state functions. So if a process is reversible, for example, A is converting to B and then B is again converting to A, that means what? That means here what will happen? Delta S will come 0. I hope that it's clear. Okay. Now see, for irreversible process, for example, A to B, if it's A to B, then it's delta S greater than 0. Okay. I hope I'm clear. Okay. Now let's see what is actually entropy. Yeah, here only we can see that. I can write here entropy is nothing but the disorderness or the randomness in a system. Let me use pinky color. Yeah, pink color. Come. It is a measure of what? It is a measure of disorderness or randomness, or you can also say that degree of mixing. Yeah, you can say that, or degree of mixing also, etc. in a system. Now there are few examples of increased entropy or decreased entropy. Okay. Actually, before writing the examples, I want to clarify something. Okay. So let's erase this part for now. Before coming there, let's do something here. If I write here, though these things also comes under example only. Okay. If I write here, any type of mixing is seen. One second. Any type of mixing is seen. Then delta S will be positive. Okay. Then entropy. Now you tell me this. Entropy of gas, liquid, solid. Whose entropy will be higher? Gas. Why? Because these molecules are more random. These molecules are less random as compared to gas. Now, in solid the molecules are closely packed. We all know that. We are not kids. Now 3. Now here you need to remember one thing. Here. If I write here 1 mole of H2, 1 mole of H2O in gaseous form and 1 mole of H2 in liquid form. Then here also it's easy. If I say this as B and this A, then we know that B is greater than A. Absolutely wrong. This is in gaseous phase, so it will be A is greater than B. Okay. Now come. Now you should remember one thing. Entropy is also proportional to the number of moles. I will give the example over here. Write one more point. Entropy is also proportional to the temperature. Here is one catch. See, if I write here 1 mole of H2 gas and 2 mole of H2 gas, then which one will have higher entropy? This one. If this is A and this is B, then B is definitely having higher entropy. Now see this point. This is important here. This point is very much important. Sorry. Yeah. But when I wrote this formula, delta is equal to delta Q reversible by temperature, then you all might ask me that here the temperature and delta is are inversely related. Then how can you say this? See, one thing. I didn't specify that here delta Q is constant. And one thing that you should remember, delta is only proportional to T if this delta Q reversible is constant. Otherwise it is not. If it is only given to you that how entropy is related to temperature, you should say if the temperature increase, delta S will definitely increase, because you can take any energies, all the energy are the function of temperature. It can be delta H, it can be delta U, it can be delta S, it can be delta G. All the energies are function of temperature. If the temperature is increased, then the entropy will increase. But if I ask you one question, if the heat in reversible process is kept constant, then lower the absolute temperature. See, absolute I am writing. Lower the absolute temperature, higher will be the entropy, or vice versa. I hope I am clear. You all got my point what I am saying. You might remember one thing. In physics also there was one thing. Q equal to Cv or C equal to what? Q by V. But this capacitance is not dependent on Q as well as V. There was one thing. Okay. It is not like that if I wrote a numerator and a denominator, then it should be dependent on these two directly or inversely. Maths doesn't tell that. Okay. This, in chemistry or in physics, this direct or this indirect relationships are generally calculated practically. Okay. Okay. Now one more thing. Entropy is also proportional to atomicity. Atomicity is basically what? I'm writing, if the atoms are more, then that will be, it will have more entropy. Okay. For example, if I write 1 mole of O2 and if I write 1 mole of O3, see here mole is constant. So now we need to check the atomicity of this compound O2 and O3. Here we can we can see 3 oxygen molecules or 3 oxygen atoms. Here we can see 2 oxygen atoms. So this will have higher entropy. Okay. Now entropy is also proportional to the molecular weight. Okay. Like if I give one question, 1 mole of N2 gas and 1 mole of H2 gas. Okay. So here A will have more than more entropy than B. N2 gas, this is 28 gram or 28 AMU will be the right thing. Molar mass can be 28 gram, but the molecular weight should be 28 mu. Here it will be 2 mu. I'm not going into that. Okay. Now in some process, I will be dealing with this process separately. Okay. But now I'm just writing it. Okay. In some process like vaporization, sublimation, melting, you all say here the entropy will be positive or it will be, I mean here the entropy will increase or it will decrease. If it will increase, it will be positive, and if it decrease, you can write it as negative. So you say that. What happens in vaporization? Vaporization is nothing but the conversion of liquid to gas. That means the space between the molecule will increase. That means the molecule will be more in a random state. Okay, in vaporization. So for vaporization it is positive. Now for sublimation, you might have seen in the temples there is one compound known as camphor. So when the purohit or when the panditji fires that camphor, we immediately see the solid getting converted to gas immediately in fraction of seconds. It is not like it is not undergoing the liquid state, or the solid is not coming to the liquid state. It is basically uh, liquid state exists for a very less time. So actually the definition of sublimation that we have studied from our young classes, I mean for our from our class 6, 7, 8 standard, is basically the conversion of solid to gas directly. So basically it doesn't convert from solid to gas directly. It have to convert into liquid first to get converted into the gas. But the liquid phase is of very small amount of time. Though this is not even, important, so I should not go in this detail. So this is what sublimation. So basically here also the distance between the molecule will increase. Eventually the molecules will be in more random state. Now for melting, what happens in melting? In melting again, what happens? Again the space between the molecules will increase. So eventually the entropy of the system will also increase. So basically here delta S will be positive. Got it? Yeah. Now for freezing and crystallization, what happens? Yeah, these things are very easy terms. Okay. Crystallization. So here it will, by the name we can understand, here it will decrease. Crystallization is also done from liquid to solid state, okay, or in semi-liquid to solid state. Yeah. Now one important thing that you should be remember, I will be explaining one of these, and the other thing you can write me in the comment section, or you can find it in your own. Okay. So it is basically boiling of egg. It's one example. The other example is entropy of stretched rubber. See, boiling of egg, we can think that in a raw egg, the yolk is in liquid form. So you might think that the molecules will be far apart from each other. Now, if you boil this yolk in the outer, and the white part will become solidified. So you can see, or you can feel like that now the molecules came close to each other. So the entropy might decrease, might be negative, or it might decrease. But this is not the case. What happens is basically a different thing. What happens is that the bonds will break. The bonds will break. And if the bonds will break, definitely the entropy will increase. Now you should also remember this thing. What happens here? I am giving this to stars. And I am removing this thing. This is looking untidy. Okay. Now see here. Entropy of stretched rubber. It is less than, it should be less than the entropy of unstretched rubber. Okay, yeah. So basically the basic idea of entropy is clear to you all. Okay, now I will come to thermal reservoir. Reservoir. A thermal reservoir basically is a very big body, or it's a very large system. Large system as if it has high specific heat capacity, along with the mass is also more. So it can, I mean, it has heat capacity tends to infinity. Okay, so it can absorb a large amount of heat. It can absorb a large amount of heat. Now thermal reservoirs from which heat is taken are known as source, and thermal reservoirs in which the heat is inserted, these are known as sink. So I am writing here, these are basically what, large system which has what, very high mass into specific heat value. Specific heat value. See guys, if any noise is coming from outside, please ignore that. Okay, focus on what I am teaching to you. From which a large quantity of energy is absorbed. Energy is absorbed or added. See, one thing I'm not writing, but you can also add this, that we can also take out a large amount of energy from there. Okay, now see, reservoir, I mean some reservoir which supplies energy, reservoir that supplies energy are what, are known as source. For example, here is one engine, and if there is a reservoir having Q1 energy, not Q1 energy, I cannot write the exact energy term for any sort of reservoir because it has a lot amount of energy at T1 temperature. It is, I mean, supplying Q1 energy to this engine. Now this engine is rejecting some of the heat and it is transferring this heat to other reservoir having T2 temperature. This thing is known as sink. This is known as source. So what I can write here, what are what are sinks? Basically the reservoir that absorbs energy in form of heat or energy, yeah, these are known as sink. Okay, now we basically build a very good foundation to study heat engines and Carnot heat engine. Okay, our foundation part is done. Now slowly and slowly we will increase the level. See, basically for today we will go up till Carnot heat engine. Maybe in some other day, I cannot promise you the date because of some reason or the other, because I also have some personal works to do. So basically today we can complete up to Carnot heat engine. Later we will deal with some of the disadvantages of second law, and we can also derive some equations. We can see some relations of entropy as a function of V and T, as a function of P and T, as a function of P and V, and then we can eventually start Gibbs free energy. So basically 2 or 3 lectures more I think I need, at least 2 lectures I need, 2 lectures at least, yeah. So now heat engines, yeah. Heat engines are basically device. See, one thing that I skipped is that there are few definitions of second law given by some scientists like Kelvin-Planck, like Clausius. Okay, you just go through those definitions by your own, because I don't feel like those definitions are very much important. Like there is one definition given by Kelvin-Planck. Over here I want to write that. Okay, but before that let's write what is heat engines. Heat engines are basically device which convert which converts what? Heat to work. See, in some books it is also written that thermal energy, basically this is nothing but heat, but they are using some catchy headings or some catchy words. Thermal energy to mechanical work. Now see, according to Kelvin-Planck, he defined the second law. As that no heat engine in the world, no heat engine in the world whose sole result is the absorption of heat from a reservoir and complete conversion of the heat to work. No heat engine can convert. So he defined the second law as, second law of thermodynamics, as no process is possible. Here process is the system and here system is heat engine. Okay, no process is possible whose sole result, sole means only, whose sole result is the absorption of heat from a reservoir and complete conversion of that heat to work. I explained this under the limitation of first law also, that this whole heat cannot be converted to work, fully. There should be some energy losses. Okay, let's reduce its size. Sorry. I can reduce its size furthermore. Yeah, this okay. Let's cover it up. I can use this pink color. So basically now I will be drawing this heat engine wala system. Okay, see, I can draw it over here. I can draw it. So basically this is the source, and this source is having T1 temperature. Okay, now here I am drawing one engine. This is the heat engine, or this is heat engine. I cannot write it over there. I can write on this side. I am writing this. See, basically students are confused that this whole system that I am going to draw, they think that this whole system is a heat engine. No, the heat engine is this one. Here there is sink, and the sink is kept at T2 temperature. Now we all know the basic phenomena that heat always flows from hot body to cold body. Now if I say, now so that's why I am writing here, just remember this thing, T1 I have taken higher temperature than T2. So T2 is basically the colder body. Now see, this heat engine is taking heat from the source. That should it take. And how much heat it is taking? It is taking Q1 amount of heat taken. It took Q1 amount of heat. Now it does some work. Definitely it does some work. What work? I wrote there mechanical work. I can write anything. And the rest heat it is rejecting into the sink. Q1 is the Q2 I should write. Q2 is the rejected heat. This is the rejected heat. Okay, yeah, now this heat engine, yeah, it's okay. So this thing will also have infinite heat capacity. This thing will also have infinite heat capacity. Now if I want to write the efficiency of this heat engine, efficiency is written as eta. So eta is nothing but output by input. So what we are getting, we are using this energy to get this work. So this is the output. Okay, now what we are putting in, we are putting this Q1 heat. Yeah, you got it what I am writing? Definitely, I hope that you got it. Now what is this W? What is this W? See it very well. See, we took Q1 amount of heat and we did W amount of work. Then the rest heat we are rejecting it into the sink. Okay, so basically Q1, from Q1 heat we did W amount of work, from Q1 heat we did W amount of work, and we reject Q2 amount of heat. So that means what? That means W equal to Q1 by Q2. Basically W is the net heat that we are getting here. Now we can write here, we all know we are not kids, so we can, this thing we can do Q2 by Q1. So this thing will be 1. So ultimately what is coming? 1 minus Q2 by Q1. Is it okay? 1 minus Q2 by Q1. Okay, this is the efficiency. See here, one thing I can write here, that eta for Carnot cycle will definitely be Q2 by Q1, but we can also write it like T2 by T1. Okay, this is for Carnot heat engine. I don't think that today I can complete this whole Carnot cycle, because Carnot cycle is a very big process. There are 4 processes happening over here. I think I need one more class to deal with this. Basically, Carnot heat engine is a hypothetical, or it's a ideal, or it is basically a ideal system that has been hypothetically created by Carnot. It says that the maximum efficiency, if it's possible by any heat engine, then that heat engine should be Carnot heat engine. Okay, I am saying the maximum efficiency is only achievable by Carnot heat engine. Maximum efficiency. I am not saying 100% efficiency is achievable. So if I give two statement, 100% efficiency is possible by a Carnot heat engine. Statement 2, maximum efficiency is achievable from a Carnot heat engine. So which statement is correct? Definitely the first statement is wrong. 100% is not possible in any way. In any way, 100% is not possible. Some amount of heat gonna lose only. So maximum energy or maximum efficiency you can get in Carnot heat engine. Okay, there are 4 processes. Basically, isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. I will be dealing with these 4 processes maybe after 2 days or after 1 day. So till then, be happy, stay good, bye.